Okay, so unfortunately, no pets today, just because today is the day where I'm stuck at the school. Like I have a class until 11:20, and then I have 1 hour in this classroom, thankfully. Okay, so what did we do previously? We finished 1.2. Oh, someone said morning. They said I am great. I'm great too. I think I'd say I'm great. I had like a 6 hour nap yesterday, and then I still was actually able to fall asleep at night. So I got a total of like 12 hours of sleep. So I'm good. Okay, so we're gonna go to 1.3, adding and subtracting fractions. I actually wanted to I wanted to start off with something a bit different, a bit of a fun math puzzle. I show this to every one of my classes because it's probably one of the most interesting math things and psychological things. It's a really, really fascinating little experiment. So we'll look at that just for fun, and then we'll go to adding and subtracting fractions. Okay, so recording still good, good. Okay, let's go to a whiteboard. Where's the whiteboard? Oh, share screen, okay. So here is the math riddle, and I'm gonna take a poll about what everyone thinks the answer is. So this is called the Monty Hall problem. It was published by a magazine in the 1970s. It was a problem where you're on a game show and you want to win a prize, and there's a bit of a debate on what is the best method for winning this prize. I'm not going to tell you much more than that because I want people to just give me their genuine opinions about what the solution is. So you are on a game show, and there are 3 doors. Behind one of the doors is a car, and you would like to win this car. Behind the 2 other doors, each of them has a goat. So I guess either way you win. Actually, I don't think a goat is a win because like no one wants a goat. You're gonna have to sell that goat. I think they're probably really smelly, but you know, I'm sure goats are pleasant creatures. Hashtag support the goats. Anyways, so let's just say 1, 2, 3. Oh, let me just see chat. Have I seen baby goats? I have. I watched the dodo on YouTube, and yeah, baby goats are cute. Yeah, any baby animal is cute. Even baby crocodiles are pretty adorable. Okay, so there's a car behind one of these, and the other 2 have, let's just say, some cute baby goats. Why not? So this is how the game works. You pick one of the doors. Let's say you pick the first one. Let's say you pick that one. You're hoping that the car is behind that one. And then what happens is that the host comes on and he opens one of the other doors. So your door, you've picked it, but for now it's just locked. You don't know what's behind it. And he's going to come along and he's going to open another door, one of the other 2, revealing a goat behind it. So he opens this one and there's a goat. And then he gives you an option. He says, if you want, you could stick with your original choice and see what is behind that door, in this case, door number 1. Or you have the option of switching to the remaining unopened door to see if you want that one. So you can stay with your original pick, or you can switch to the remaining unopened door. And the question is, does switching increase your chances of winning the car? Is it advantageous to switch, or does it not make any difference? So I'm going to go back to the chat, and I want to ask everyone, so if you think it makes a difference, say yes. If you think it doesn't make a difference, say no in the chat. Let's see what the opinions are. So does it make a difference? 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 Okay. Come on, let's get some contrarians in here. Someone say yes, just there we go. Peyton said yes. So we got about almost all yeses, two yeses, and the rest are no's. I don't think so, but I also see how it could possibly. So we got kind of an unsure. So very interesting results. These are always the results that I get, and it just constantly fascinates me. So the answer is always very surprising to people. The answer is that switching doors will double your chances of winning the car. And this method, this solution that they presented, it's so counterintuitive that they actually study this in college and university, like in psychology classes, just as examples of counterintuitive situations. So the answer is actually yes, it doubles your chances of winning. And most people say no. Let's see. Someone said they wanted to say yes, but all the no's made them second guess themselves. I'll assume you said yes. I'll give it to you. So there's a fascinating history behind this. So yes, 1970s. I think it was some magazine that published it. They published the initial problem, and then they published the solution. Someone said learned this in the movie 21 about card counting. I don't think I've ever even heard of that movie. Darn, I thought I was the only one who knew about this cool little puzzle. Yeah, so then when the magazine presented the solution and claimed that switching doubles your chances of winning, there were 1,000 mathematicians who wrote into the magazine disagreeing with their solution, disagreeing that switching gives you an advantage. Even among those mathematicians was actually one of the greatest mathematicians in history called Paul Erdős, who was a homeless Hungarian man who did math for like 70 years, and he lived out of 2 briefcases. He gave away all of his money to charity. Even Paul Erdős disagreed with the solution. So the solution is so counterintuitive that even 1,000 PhD mathematicians wrote them and said, nope, switching does not give you an advantage. And eventually they were proven incorrect. There are various proofs that switching does offer an advantage. So it's a super, super fascinating puzzle. And just for clarity, I'll provide 2, I don't know if you can call them proofs. I'll provide 2 illustrations to illustrate that switching actually is advantageous. So let's look at a more extreme case. And when you look at a more extreme case, it becomes a little more clear that switching is what you want to do. Let's do 10 doors. Let's pretend that there's 10 doors. 1, 2, 3, 4, 5. So that's 10 right there. Okay, so let's say there's a car behind one of these and goats behind all the rest. So in this case, let's say you pick door number 1, hoping there's a car behind that. And then the host comes on and he looks at all of these doors right here, except for the one that you picked. That one is kind of locked at this point. And then what he does is he opens this one, reveals a goat, opens this one, reveals a goat, opens this one, 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 and he gives you the option of switching to that one. So most people in this case would definitely switch, because when you originally picked your first door, you had no information about what was behind it or what the chances were of a car being behind it. So your original door, it only had a 1 in 10 chance of actually being picked. But in this more extreme circumstance, you could see that all of these doors are being disqualified, and all of those percentages are going to the one remaining door that the host chooses to remain closed. Because when you pick your original door, it's no longer considered for opening. It just sits there and it's locked. So you get no further information about this. An even more extreme case would be if there were 1 million doors. So imagine picking the first door and then the host opens almost all the other doors except for one. In that case, you definitely want to switch, because he just took all those possibilities and put them into one door. But your original door, you got no info about that. It's not really advantageous to stick to it. So that's one illustration that most people accept. And then there's another proof that, not to brag, but I came up with that is so simple that I just could not understand why it wasn't online. So what you could just do is look at it on a case-by-case basis. Let's just look at a specific case. 1, 2, 3. Let's say you got a car right here, you got your goat right here, and you got another goat right there. So let's compare the situation where you never switch, and let's see what your chances are. And then we'll compare it to when you always switch, and we'll see what your chances are. So let's look at case one. Case one is never switch, and we'll see what our chances are. Never switch. So for case one, whatever door you pick is the door you end up with. So it's just a straight up 1 out of 3 chance. Because yeah, you pick a door, you end up opening that. There's 3 doors. So in that case, 1 out of 3 chance of getting your car if you choose to never switch. On the other hand, if you always choose to switch, let's see what happens. So case 2, always switch. So let's look at the 3 cases because there's 3 doors. So 1, 2, and 3. And let's go through these. So let's say you initially pick the correct door. In that case, if you switch away, you're going to lose the car. So in that first case, that's a loss. But in the other 2 cases, if you pick the second door, the host will open a remaining goat door, and then you'll actually switch and win the car. So that one's a win. And even with the other goat door, same thing. You pick a goat door, the host opens the remaining goat door, and then if you switch, you get the car. So if you compare the 2 cases, never switching only gives you a 1 out of 3 chance, while always switching, you actually win 2 out of 3 times. So you actually doubled your chances of winning by switching. So it's called the Monty Hall problem or the Monty Hall paradox. And it's super interesting. Yeah, it's a very interesting psychological test and paradox. And there are some people who just refuse the solution, regardless of any proofs, or even I think Paul Erdős only accepted it when they ran a computer simulation for him, and it consistently showed that switching is advantageous. So even Paul Erdős, who did 800 math articles and was super smart, and when he was 4 years old, he could multiply 4-digit numbers in his head. Even this tricked him. So I always like presenting it to teach class because I just think it's interesting. Okay, so that was fun. Let's do some, and I'll check out that movie 21. I've always been meaning to learn how to count cards, and I am allowed to say that because it's 100% legal, but I just haven't gotten around to it. I do know some people who do count cards and make consistent profits off of it. But yeah, it's perfectly legal because they can't make it illegal for you to think particular thoughts in your head. Okay, so hopefully everyone enjoyed that. Now let's go to adding fractions. And still recording, good. Okay, so previously we did multiplying and dividing fractions, which was surprisingly not bad. It was, there were pretty simple rules for that. But also surprisingly, adding and subtracting fractions, it's more difficult than multiplying and dividing them. It does require a bit more work. So, and there's a bunch of steps we got to go through. So everyone just bear with me. And if it doesn't make perfect sense right away, we're going to practice a lot of them. Okay, so we're going to start off with the easiest possible case, which is where you're adding up 2 fractions where they happen to have the same bottom number. So in this case, you have 1/10, you add 2/10, and surprise, surprise, you get 3/10. And that's basically all you have to do when the bottom number happens to be the same. Because like with our pizza analogy, you're just dealing with a pizza sliced up into 10 pieces. And then you take 1, you take another 2, and you got 3. You got 3/10. So if you wanted to get really formal with this in regard to the rule would be that the bottom number just stays the same the whole time, even for the answer. And then for the top numbers, you just add them up. And so that's what you do when you have, as they say, quote, a common denominator, end quote. And yeah, because in this case, again, all the slices are the same. So you're just adding up slices. That's why the bottom number, it doesn't change. So that's easiest possible case. Not much else to say about that one. Let's do one more for that one. So you have 2/8. and then you add 3/8, and then you add 4/8, and then you get 9/8. So again, the 8 just stays the same. The 8 will even be the same in the answer, and then you just add up the top numbers, and 9/8 is your answer. But then the additional problem arises: how do we add fractions when they don't have the same bottom number? Here's an example: 1/2 plus 1/3, which was just the simplest one I could think of. How the heck do we add those together? Because half of a pizza, the size is not comparable to a third of a pizza. And you're not allowed to just add the top and add the bottom, because that does not work. So what you got to do is you got to rewrite each of these fractions so that they have the same values as what they previously had, but that they have the same number on the bottom. So what you want to do is you want to first decide what that number is going to be. And that's going to be, quote, your least common denominator. So the way you pick that is you look at 2 and you look at 3 and you ask yourself, what is the smallest number that happens to be a multiple of both of those numbers? I'm going to switch to a whiteboard just for the solution. Whiteboard. 1/2 plus 1/3. So that is the first step. So what do we think? So what's the lowest number that's a multiple of 2 that's also a multiple of 3? Someone said 12. 12 is 12 works, but it's not the lowest. So 6, Steph is right. 6 is actually the lowest. And if you're really desperate to try to figure it out, you could just kind of brute force it. There's various methods we'll look at, but like if you wanted to brute force it, you could literally just list the multiples of 2, 2, 4, 6, 8, 10, bunch after that. And then you could just list the multiples of 3, 3, 6, 9, 12. And then you just look at the lowest number that's common to both lists. And you got a 6. So that's one method. That's not my preferred method because I don't like brute force methods where you just list stuff. I like more elegant methods than that. But I think we'll do the full question, and then later we'll look at some additional methods. So that's the first thing you do. You pick your least common denominator. So let's list that LCD as 6. Okay. So far, so good. And now the next step is, like I said, take each of these, rewrite them so that they have a 6 on the bottom, but that you're not actually changing their value. Yeah, so let's do these one at a time. Let's do 1/2. Okay, so we have got 1/2, and we want a 6 on the bottom. So let's just start there. So 2 times what number equals 6? 3, of course. So what you do is you multiply the bottom number by 3 so that you'll get a 6 on the bottom. But remember, one of our rules is that whatever you do to the bottom number, you have to do to the top number so that it stays the same as what it was. So you also got to multiply the top number by 3. And in this case, I'm using 3 because, again, I just asked myself 2 times what number equals 6, and I just pick whatever number works, and it's usually pretty clear. So this will become 3/6. And that's perfectly good because 1/2, it's the same thing as 3/6. 3 is half of 6, of course. So it is the same fraction, but now, thank goodness, you have a 6 on the bottom. And then you do the next one. So 1/3. So you ask yourself, so you always look at the bottom number first because that's the one you're mainly concerned with. So you ask yourself 3 times what number would give you 6. And whatever that number is, that's what you use at the bottom. And you always use multiplication. So this would be 3 times 2. And then same thing on the top, multiply it by 2. So it's always the same number on the top and the bottom, but which number is dictated by the bottom and trying to get to that common denominator. So that's 2/6. Good, good. And that's the same as 1/3 because 2 is a third of 6. So that's good. So now we finally have equivalent fractions, but now we have common denominators, and now we can just add them up. So 3/6 plus 2/6 will give us, so the bottom number always stays the same when you have that common denominator, and the top number in this case is going to be 5. So therefore 5/6 is our answer. So basically we're just like recontextualizing the fractions, not actually changing them, but just, basically changing them so that they have the same size of slices, but they're still the same amount of pizza, if that makes sense. And actually, for this question, there's a good illustration we could do. Just give me a second to visualize it. That, and then that, and then that, and then that, and then that. Okay. Yeah, so here's the illustration. Let's look at 1/2. We're just going to use the pizza analogy, and we'll just kind of show the logic that's being used here. Here's a pizza. Yummy. Here is half of a pizza. So by changing 1/2 into 3/6, all you're really doing is kind of just slicing up the pizza, like, let's say like this. And you're just taking these slices. So it's still half a pizza. You're just viewing it as 3/6, as 3 slices out of 6. Because if you think of it in sixths, you could actually add them up. So that's kind of what you're doing when you're messing around with these fractions. You're not actually changing them. And then for the, what was the other one? For the 1/3, let me try to draw that. Let's say the 1/3 is right here. For the 1/3, we change that into a 2/6, which is basically just like doing this. And then if you count them, you got 1, 2, 3, 4, 5. You got 5 out of 6. This is definitely not proportionate. This slice is way too big. I drew this incorrectly, but that's the logic that we're using. It's like we want the same size slices. We rearrange stuff, we change stuff, and then we can finally add them up. So there is a visual logic to what we're doing. I always try to visualize everything. Otherwise, in my mind, none of it really means anything. Okay, so hopefully everyone, we'll do a few more, obviously. Hopefully everyone kind of sees the logic that we're using here. Let's do a few more. Hold on, let me just activate my laptop. Okay, what's another good one? So we got that one. Oh, that's a good one. So 3/4 plus 1/5. Oh, there is a PDF of these, and there's like a million of them. I spent like 5 hours on it. I don't know why I spent so long on it, but that was like 5 years ago, so it was an investment. So check that out. That's under extra material. 3/4 plus 1/5. So let's do this one. First step is figure out your common denominator, smallest number that is a multiple of 4 and also a multiple of 5. And for this question, let's go through some methods for this. So let me think for a second. So we did the brute force method, which is where you just kind of list multiples of each number and then you just compare the lists. I don't like that method because like what happens if your lists end up being like a mile long? In my mind, the best method is look at the bottom numbers and pick the largest one, in this case 5, and start there. Pick 5 and see if 5 works. In this case, it doesn't work because it's not a multiple of 4. And then start going through multiples of 5 and just see what the first one is that works. So 5, 10, 15, 20. So in this case, 5 doesn't work, 10 doesn't work, it's not a multiple of 4, 15 doesn't work, but 20 works. So 20 is what you use for your least common denominator in this case. And that's my favorite method because it just seems like it's a lot less to worry about. So I just focus on the largest one. I cycle through multiples of the largest one. And then when I hit one that works for both bottom numbers, then that's what you use. And I think that's the method that most people end up using, but everyone kind of comes up with their own. So LCD is 20 in this case. Good, good. And now let's rewrite each of them. Let's start with 3 over 4. So big question, 4 times what number gives you 20? That would be 4 times 5. Let's see. Yep, exactly. So let's multiply this. Let's multiply the bottom by 5. And remember to multiply the top by 5 as well. You're obligated to do that. And you end up getting 15 over 20. It's basically the opposite of reducing to lowest terms. It's actually like going up to higher terms. So it's kind of similar. It's kind of just the opposite of reducing to lowest terms. And now let's do the next one, 1 over 5. So you ask yourself, 5 times what number gives us 20? And it's 5 times 4. So you use 4, and you use 4, and you get 4 over 5. Or wait, no, that's not right. 4 over 20. Yeah, 4 over 20. It looks so ugly. 4 over 20. Okay, that's fine. And then last step is add them up. 15 over 20 plus 4 over 20. 19 over 20. And I saw that in the chat, so whoever wrote that was correct. What else can I say about these? There is a, go ahead.
Do we have to show our work on our assignment to tell you how we found out the lowest common denominator?
No, not really. If you just state it, that's fine. Because I realized that a lot of the times you could basically just do it by observation. So for a question, basically I would like you to, at least just state the least common denominator, show how you rewrote your fractions, and then just add them up. Just a reasonable amount of work so I know that the person generally knows what method to use. And just keep in mind that like sometimes people will just write the answer, and I really don't like that. Sometimes I'll take marks off just for the fact that they didn't show any work, but a lot of the times they'll lose marks because like for this question, a lot of people, they'll show no work and they'll say that the answer is 17 over 20. And it's like, I can't give any marks for that because the answer's wrong. I don't know if it was an arithmetic mistake. I don't know if the entire method was wrong. So showing work is always good because I always want to be able to give partial marks, even if the answer is wrong. What else? Oh, and then there's a couple other things. Oh, so let's go through a couple of common mistakes that everyone makes. So one common mistake, which is understandable, is at this point in the question at the end. Sometimes people, instead of keeping a 20 on the bottom, they'll add up the 20s and they'll conclude that the answer is 19 over 40, but you don't do that. It just stays as 20. Again, these represent slices and the size of the slice is not changing. So don't add the bottom number in that regard. Then there's another mistake that is one of those mistakes that breaks my brain. And let's look at that. So whoever made that original mistake all those years ago, they are responsible for the fact that I have a broken brain. Okay, so let's look at this one. So the common mistake is that someone will just do this. They'll just add the top numbers and they'll add the bottom numbers. And no, you can't do that. That's wrong. Please don't do that. There's no reason why it would be right. It doesn't really, like, I understand that the person is trying. I appreciate that, but it's just not correct. I think the reason I see this a lot is because people are confusing this with multiplication, because multiplication is like the easier one. Addition is the one that requires all these steps. And I think people confuse them and they think that addition is the easier one. And they basically use the method that we use for multiplication, except they're using addition. But this right here, you cannot do it. It doesn't make sense. Yeah, exactly. In this case, the common denominator, or the denominator for both of these, they're not the same, so you can't do this. Plus, there are other examples that show that even aside from that logic, there's examples that show that this just does not work at all. Let me show you an example. Let's see. Let's just do 1/2 plus 1/2. And let's say that you mistakenly were going to use this incorrect method. So we'll use the method and then we'll show that it just blatantly leads to nonsensical results. So let's say that you used this incorrect method. You added the top numbers, you added the bottom numbers, you got 2/4, and then you can reduce that to 1/2. So you've somehow taken 1/2 and added 1/2 and gotten 1/2. It would be like the equivalent of taking half an apple, adding another half of an apple, and somehow ending up with half of an apple. So if you're wondering if this method works, it's very easy to see that it doesn't work, because you could come up with a billion counterexamples, and they just do not work at all. Yeah, and let's see. In this case, the correct answer would just be, well, this already has a common denominator, so you would just keep 2 on the bottom, add up your 2 on the top, and you would get 2/2, which is equal to 1. That would be the right way of doing it. That one's an easy one because it already has a common denominator, but this is just illustrating that this method right here, it absolutely does not work. So yeah, so when you're doing addition, maybe the easiest way to remember, and this is going to sound like, just remember that addition is the one that kind of sucks and multiplication is the one that's kind of easier. And I realize that's a crude way of remembering it, but it's the easiest way to remember it. When you're writing a test, just be like, oh, right, addition's the one where you got to go through like all those steps and it's a bit more work. Okay, it's that one. Yeah, or remember it however you can. What else do we have? Let's, so we got a couple minutes. Let's do one, since we were talking about coming up with the least common denominator, let's look at a neat method for that. It is called the prime factorization method. And then we'll call it a day. Oh, did I tell you guys that the other day, I think I told you this, but I can't remember. The other day I tried to introduce my Python to my bunny rabbit, and bunny rabbits, they like to boop stuff with their nose to check it out. So Amy booped my Python with her nose and scared him away. And he seemed like upset that she booped him too hard. I can picture, if Banana could talk, I could just like picture him crying and just being like, why did she have to boop me so hard? And I'd be like, buddy, she was just being friendly. And he's like, no, she did it on purpose. Like I could just totally picture the conversation, and it's hilarious. Poor Banana. Banana's my Python. Okay, and I lost him yesterday. It took me an hour to find him. Okay, anyways, I keep getting distracted. So let's look at another very neat way of finding a least common denominator. Let's say we have these fractions, 1/6, 1/4, and 2/15. So let's find a common denominator. That's of course concerning the 6 and the 4 and the 15. Now this method, the prime factorization method, requires a bit more work, but it's an algorithmic method, which means it's always the same. It's basically like a formula, and you'll always get the right answer. So what you do is you take each number and you break them down into their factors, which we looked at in 1.1. And remember, I mentioned that if you take a number and you break it down into its factors as far as it can go, it'll have all prime factors. So let's do that. Let's break these down. So 6 is equal to 2 times 3. And those are both prime, so you don't have to break it down any further. 4 is 2 times 2. Again, those are both prime, so that's good. 15 is 5 times 3. Good. And actually, sorry, in this case, I want to write 3 times 5, even though it's the same thing, just for something that we're going to do in a minute. So you break these all down into your prime factors. And then what you do is you come up with the minimal string of numbers that contains all of these prime numbers, but the minimal string. So for example, let's start with the lowest numbers. There's a 2 times 2, so we need a 2 times 2 in there. So let's write that, 2 times 2. We also need, if you look at the 6, we need a 2 times 3. but you already got a 2 in there already. So you could just do times 3, because technically you do got a 2 times 3 right there. So again, the minimal amount of numbers that you need. The last one is 15, which is 3 times 5. There's already a 3 in there. So we'll just write times 5. So if you look at this one, we do have that. If you look at this one, we do have that. And if you look at this one, we do have that as well. So it's the minimal amount of numbers, which means it will be the least common denominator. And it has all of their factors, which means by definition, it'll be divisible by all these numbers. So the answer is 2 times 2 times 3 times 5, which is 60. So 60 would be your least common denominator in this case. Someone wrote something, but I'm just not sure exactly what they mean. So yeah, in this case, 60 is your answer for this one. So it's a really cool method because it always works, and dealing with prime numbers is always cool. And yeah, what else can I say about that method? Most people don't bother using it because these questions are designed to be, you know, they're always designed to have nice answers. If it was me and I had this question, I would just use my own personal method, which is where you look at the largest number at the bottom and you start cycling through multiples of that. So like 15, 30, 45, 60, 75, and you just pick the first one that works. 15 doesn't work for 6 or 4. 30 doesn't work for 4. 45 doesn't work for either of them. 60 works for all of them. So I just like using the largest number. It just seems like there's less to keep track of. So you have a very large amount of different methods for finding the least common denominator. No shortage of methods. Let's quickly, just so we could say that we technically, let's do one subtraction question and then we'll be done. Because the subtraction questions are exactly the same. The only difference is that you subtract the top 2 numbers. So let's do one of those. 3 over 4 minus 2 over 3. Okay, so go through the same steps, find your least common denominator. I think this is one where you could just do it by observation. 12 would work for both of them, and there's no lower number that works. So yeah, most people are guessing 12. So let's do LCD equals 12. And now let's rewrite each of these. So let's take 3 over 4. So 4 times what number equals 12? That would be 3. So times 3, and then do the same thing on the top. So that's 9 over 12. Comma, and then you got 2 over 3. And you want to do the same thing. So 3 times what number will get you to 12? And that's 4. And multiply by 4 on the top as well, and you get 8 over 12. So again, exactly the same. And then at the end, you just subtract them. So 9 over 12 minus 8 over 12 equals 1 over 12. So yeah, really, there's no difference between adding and subtracting fractions other than the fact that for one, you're adding them, and for the other, you're subtracting them. What time is it? 12:13. I guess that's a good place to stop. Does anyone have any questions? The first assignment is up, but it's just up early. So once we finish the chapter, then we'll come up with an actual due date. But you can work on some of it, of course. You know, it's up to you. What else? Yeah, I guess there's just not much for this class. Like I always feel like I'm forgetting something, but I don't think I am. Assignment, no test soon. Okay, cool. Oh, let me finish with the attendance. I already took most of it. Usually if I'm a few minutes late, it's just because I'm doing the attendance. Okay, I think I have everything. This person. Do. This person. Got them, got them. Oh, I need this one. Anyone see any good shows lately? I haven't been able to find a show that interests me in like a year, and it's driving me crazy. Oh, I should pause the recording if I'm gonna